Look up at the night sky, really look, and let your eyes linger on those shimmering pinpricks of light. Each one is not just a star, but a living, breathing chapter in the universe's greatest story. They burn, they evolve, and in their final moments, they scatter the very ingredients that make up everything around us, your body, your planet, even the air you breathe. This isn't just astronomy, it's a family album of the cosmos, and every one of us is written into its pages. Welcome to Stellar Destinies, where we'll trace the lives of stars from their fiery births to their spectacular deaths, revealing how these celestial titans shape the fate of galaxies, planets, and life itself. Think of the universe as a vast, interconnected web, where the fate of a single star can ripple across billions of years. Take our own sun, a seemingly ordinary star, yet without its steady glow, Earth would be a frozen wasteland, and life as we know it would never have sparked into existence. But stars aren't just passive beacons, they're alchemists, forging heavier elements in their cores and seeding the cosmos with the building blocks of planets, oceans, and even DNA. When a massive star dies in a supernova, it's not just an end, it's a cosmic rebirth, scattering stardust that will one day coalesce into new worlds. This journey isn't just about distant suns, it's about us. The iron in your blood, the calcium in your bones, these elements were forged in the hearts of long-dead stars. You are, quite literally, made of stardust. And that's the magic of Stellar Destinies. It's a story that ties the grandeur of the cosmos to the intimate details of our own existence. Over the course of this video, we'll explore stellar nurseries where stars are born, witness the dramatic deaths of supergiants, and follow the trail of stardust as it weaves its way through the universe's history. Buckle up, we're about to embark on an adventure that stretches from the first stars to the far future, revealing how the lives of these celestial giants are forever entwined with our own. Deep within those swirling cosmic clouds, where temperatures plunge hundreds of degrees below zero and darkness seems absolute, something extraordinary is happening. These aren't just empty voids, they're stellar nurseries, bustling factories of creation where the universe crafts its next generation of stars. Picture the Orion Nebula, a glittering tapestry of gas and dust visible even to the naked eye. What looks like a faint smudge of light is actually a maelstrom of raw material, a place where gravity patiently sculpts chaos into cosmic order. Over millions of years, pockets of gas grow denser, pulling in more material until the pressure at their cores becomes unimaginable. Then, like flipping a switch, nuclear fusion roars to life. Hydrogen atoms slam together, forging helium and unleashing the energy that makes a star shine. But not all stars are born equal. The mass a star gathers in its infancy becomes its cosmic fingerprint, dictating everything from its color and temperature to its ultimate destiny. A modest star like our Sun, born with just enough mass to sustain steady fusion, will burn calmly for billions of years. Meanwhile, a massive blue giant dozens of times heavier blazes through its fuel at a breakneck pace, living fast and dying young. And the tiniest stars, red dwarfs so faint they're nearly invisible, might outlast the universe itself, glowing faintly for trillions of years. It's this incredible diversity that makes stellar nurseries so vital. They're not just birthing stars, they're writing the first lines of each star's life story. What's truly mind-blowing is how these nurseries don't just create stars, they shape the future of entire galaxies. The heaviest stars, though rare, become the universe's powerhouses. Their fierce radiation carves cavities in the surrounding gas, triggering new waves of star formation like cosmic dominoes. Their eventual deaths, as we'll see later, will seed the cosmos with heavier elements: carbon, oxygen, iron, the very stuff of planets and life. Meanwhile, the humbler stars provide stability, anchoring solar systems and bathing their planets in steady light for eons. Every star's journey begins here, in these quiet, cold clouds, where gravity's patient pull sets in motion events that will echo across space and time. Once a star settles into the main sequence, it enters the most stable and predictable chapter of its existence, a cosmic balancing act that can last longer than entire geological eras on Earth. Imagine a tightrope walker perfectly poised between two opposing forces, gravity relentlessly pulling the star's material inward, while the intense pressure of nuclear fusion pushes outward. This equilibrium isn't just a fleeting moment, it's a marathon, with stars like our Sun maintaining this delicate dance for billions of years. During this phase, the star becomes a reliable anchor for any planets orbiting it, offering a steady stream of light and warmth that can nurture the delicate chemistry of life. The Sun, that familiar golden orb in our sky, is the ultimate poster child for main sequence stars. Every second, it transforms millions of tons of hydrogen into helium deep within its core, releasing energy that has sustained Earth's biosphere for over 4 billion years. But what's fascinating is how this stability hides a dynamic interior. The Sun's core is a roiling furnace, where temperatures soar to 15 million degrees, yet its surface, the photosphere, appears calm and unchanging to the naked eye. This stability is a gift to planets like ours, providing the consistent conditions needed for oceans to form, climates to stabilize, and life to emerge. Not all main sequence stars are created equal, though. Their characteristics like color, brightness, and lifespan are dictated by their mass. Take a star like Sirius, the brightest star in our night sky. It's roughly twice as massive as the Sun, burning hotter and bluer, with a lifespan cut short by its extravagant energy output. Meanwhile, a humble red dwarf, with just a fraction of the Sun's mass, might sip its hydrogen fuel so slowly that it outlives every other star in the galaxy. This diversity means that main sequence stars don't just light up the cosmos, they shape it in wildly different ways. Hot, massive stars flood their surroundings with ultraviolet radiation, sculpting nearby gas clouds and triggering new star births, while cooler, smaller stars provide the long-term stability needed for planetary systems to thrive. What's truly remarkable is how this phase, as stable as it seems, sets the stage for everything that follows. The elements forged in a main sequence star's core, helium, traces of lithium, and beryllium, are just the beginning. Later, as the star ages and exhausts its hydrogen, these elements will become the building blocks for more complex reactions. But for now, during this golden age of equilibrium, the star is content to shine steadily, a beacon of constancy in an ever-changing universe. And in that constancy, planets find their orbits, climates settle into rhythms, and life, against all odds, finds a way. Even the most stable stars can't burn hydrogen forever. When that fuel runs low, the star's core begins to contract under gravity's relentless pull, triggering a dramatic chain reaction. The rising temperatures ignite a shell of hydrogen around the core, while the star's outer layers balloon outward in a fiery rebellion against collapse. What was once a modest main sequence star like our Sun transforms into a red giant, a swollen, luminous titan that could engulf planets in its expanding embrace. Take a star like Aldebaran, the fiery eye of Taurus. From Earth, it appears as a gentle orange glow, but up close, it's a churning inferno hundreds of times wider than our Sun. Its outer layers, now far from the core, cool to a reddish hue while the dying embers within grow hotter, fusing helium into heavier elements like carbon and oxygen. This is stellar alchemy in action, a process that will eventually lace the cosmos with the raw materials for rocky planets, breathable atmospheres, and even the molecules of life. For truly massive stars, the expansion phase becomes even more spectacular. Supergiants like Betelgeuse don't just grow, they become cosmic leviathans, stretching so wide that if placed at the center of our solar system, their surfaces might brush past Jupiter's orbit. Their brilliance defies imagination, outshining entire galaxies of smaller stars, yet their fate is sealed. The very elements they forge, silicon, neon, iron, will become the seeds of their destruction. Every atom of oxygen in your lungs, every speck of carbon in a diamond, was born in the heart of such a star during this fleeting, fiery chapter. What's astonishing is how these bloated giants shape their surroundings long before they meet their end. Their intense stellar winds, rivers of charged particles, blow outward for light years, carving vast bubbles in interstellar space. These winds carry stardust like cosmic confetti, sprinkling heavy elements into the void where future generations of stars and planets will form. The red giant phase isn't just an ending. It's a cosmic relay race, passing the torch of creation from one stellar generation to the next. Yet for all their grandeur, these stars are living on borrowed time. The helium in their cores won't last forever, and when that too runs dry, the final act of their lives will begin. But for now, they burn as radiant beacons. Their swollen forms a testament to the universe's endless capacity for reinvention. They remind us that even in the twilight of a star's life, the cosmos is hard at work, crafting the ingredients for worlds yet unborn. When a star like our Sun exhausts its nuclear fuel, it doesn't go out with a bang, it fades with a whisper. The outer layers, once a seething red giant, drift away in a shimmering veil of gas, forming what astronomers call a planetary nebula. At the heart of this glowing cloud lies the star's collapsed core, now a white dwarf, a dense, Earth-sized ember packing half the Sun's mass into a sphere no larger than our planet. Imagine compressing a mountain into a sugar cube, and you'll grasp the staggering density of these stellar remnants. A single teaspoon of white dwarf material would weigh as much as an elephant, held together by a quantum force so powerful it defies ordinary physics. For centuries, white dwarfs puzzled astronomers. The first one discovered, Sirius B, orbited the brightest star in our night sky, yet remained invisible to telescopes until the mid-19th century. When astronomers finally detected it, they were stunned. A star as massive as the Sun, radiating almost no light. Today, we understand these faint objects as the final resting place of 97% of all stars in the universe. They're not truly white either. As they cool over billions of years, their color shifts from blue to yellow, then red, like a dying ember in a cosmic campfire. What's extraordinary is how these silent giants still shape the cosmos. Their intense gravity can strip material from companion stars, sparking sudden thermonuclear explosions called nova. Some white dwarfs, greedily accreting too much matter, reignite entirely in catastrophic supernova, scattering freshly forged elements across space. Even in isolation, their slow cooling illuminates the universe's timeline. The oldest white dwarfs act as cosmic clocks, helping astronomers measure the age of our galaxy. Yet their most profound legacy might be what they leave behind. The expelled layers of a dying star, rich in carbon and oxygen, become the raw materials for future planets and life. Every pencil's graphite, every breath you take, carries atoms forged in stars like ours, then gently returned to the cosmos by white dwarfs. These fading cinders remind us that death in the universe is never truly an end. It's a transformation, a passing of stellar wisdom to whatever comes next. But for the universe's most massive stars, death isn't a quiet fate, it's a spectacle of unimaginable violence. When these giants exhaust their nuclear fuel, their cores collapse in less than a second, triggering an explosion so powerful it can outshine 1 billion suns. This is a supernova, nature's ultimate fireworks display, where a single star briefly rivals the light output of an entire galaxy. Picture the Crab Nebula, the remnants of a supernova observed in the year 1054. Chinese astronomers recorded it as a guest star, so bright it was visible in broad daylight for weeks. Today, nearly 1,000 years later, the expanding debris still glows, a testament to the raw power unleashed in that moment. What happens inside a dying star to create such chaos? As fusion grinds to a halt, the star's iron core, now more like a ticking time bomb than an engine, suddenly implodes under its own gravity. Atoms are crushed together so violently that protons and electrons merge, forming a dense neutron soup. The collapse rebounds in a shockwave that blasts outward at nearly 1/10 the speed of light, shredding the star's outer layers and flinging them into space. This is where the magic happens. The incredible heat and pressure forge elements heavier than iron gold for jewelry, uranium for nuclear reactors, even the iodine in your thyroid, all created in the heart of this stellar inferno. Supernova don't just destroy, they create. The shock waves from these explosions slam into nearby gas clouds, compressing them until new stars ignite like cosmic dominoes. Our own solar system might owe its existence to a long-dead star's violent end. The heavy elements in your phone, your car, even your bones were likely forged in a supernova that exploded billions of years before the sun was born. These explosions are the universe's recycling centers, turning dying stars into the raw materials for new worlds. Perhaps the most astonishing legacy of supernova lies in their aftermath. Some leave behind neutron stars city-sized spheres so dense that a sugar cube's worth would weigh as much as Mount Everest. Others, the very heaviest, collapse into black holes, warping space-time itself. Yet even in death, these stars keep giving. The elements they scattered become part of interstellar clouds, then new stars, then planets, and perhaps on some distant world, another civilization looking up at the night sky, wondering about the origins of their own stardust. The cycle continues, relentless and beautiful, written in the ashes of exploded giants. When a supernova's fury subsides, it leaves behind one of the universe's most extreme objects, a neutron star. Picture taking the entire mass of our sun and crushing it into a sphere no wider than Manhattan. The result is so dense that a single sugar cube of its material would outweigh Mount Everest. This isn't just compact matter, it's nature pushing the limits of physics, where atoms themselves collapse into a sea of neutrons packed tighter than sardines in a can. Some neutron stars reveal themselves as pulsars, flashing like cosmic lighthouses with precision that would put atomic clocks to shame. Take the famous pulsar in the Crab Nebula. It spins 30 times per second, its twin beams of radiation sweeping across space with metronomic regularity. These spinning marvels aren't just celestial oddities. They're navigation beacons for interstellar travel concepts and natural laboratories testing Einstein's theories under conditions impossible to recreate on Earth. The surface of a neutron star is a landscape of extremes. The crust, harder than diamond, floats atop an ocean of superfluid neutrons that flow without friction. Magnetic fields surrounding these objects are so intense they could strip the information from every credit card on Earth from halfway across the solar system. When two neutron stars collide, an event astronomers detected in 2017, the resulting fireworks forge gold, platinum, and other heavy elements in quantities that dwarf our planet's entire reserves. What's truly remarkable is how these stellar corpses continue shaping their cosmic neighborhoods long after their death. Their gravitational influence can disrupt nearby star systems, flinging planets into interstellar space or triggering new waves of star formation. The radiation from young, hot pulsars illuminates surrounding gas clouds like celestial spotlights, creating some of the most beautiful nebulae visible through telescopes. Neutron stars represent nature's ultimate recycling program, taking the remnants of a dead star and creating objects that influence galactic chemistry for eons. They remind us that even in the universe's most violent endings, there's potential for new phenomena, new elements, and new mysteries waiting to be unraveled. Among all possible stellar fates, none captures our imagination or warps reality itself quite like a black hole. When the most massive stars collapse, they don't leave behind a neutron star's dense remnant. They carve a hole in space-time so deep that the universe's rules break down. Picture throwing a rock into the air, except this rock never comes back, no matter how hard you wait. That's a black hole's event horizon, the point of no return where gravity's grip becomes absolute and even light surrenders to the abyss. Take Cygnus X1, the first black hole ever confirmed. From a distance, it looks like an ordinary binary star system, but one member isn't a star at all, it's a silent predator, devouring gas from its companion. As material spirals inward, friction heats it to millions of degrees, creating X-rays that betray the invisible monster's presence. This cosmic dance reveals a startling truth. Black holes aren't just vacuum cleaners of the universe. They're dynamic engines capable of powering some of the brightest phenomena in the cosmos. What happens inside a black hole, we may never know for certain. Einstein's equations suggest matter collapses into an infinitely dense singularity, a place where time stops and space becomes meaningless. But here's the twist. While black holes destroy information, they also shape galaxies on scales we're only beginning to understand. Supermassive black holes, millions to billions of times heavier than our Sun, lurk at the hearts of most galaxies, including our Milky Way. Sagittarius, a star, our local giant, sits quietly now, but its gravitational pull orchestrates the orbits of countless stars, maintaining order in a swirling stellar metropolis. The relationship between black holes and galaxies is a cosmic chicken and egg puzzle. Do galaxies form around black holes, or do black holes grow within them? Evidence suggests they evolved together, with the black hole's gravity influencing star formation rates and the galaxy's gas feeding the black hole in turn. When these behemoths feast, they trigger quasars' beacons so luminous they outshine entire galaxies, visible across the universe. These outbursts can blow away star-forming gas, effectively putting a galaxy's growth on pause. Yet black holes aren't just destroyers. Their mergers send ripples through space-time itself, gravitational waves that scientists first detected in 2015. These collisions release more energy than all the stars in the observable universe combined, yet they distort space-time by less than the width of an atom, a whisper of the cosmos's most violent events. Perhaps the most humbling thought is this: every black hole began as a star that lived, burned, and collapsed, leaving behind a gravitational footprint so profound it bends the universe to its will. They remind us that even in death, the most massive stars continue shaping the cosmos, weaving the fabric of galaxies and challenging our understanding of reality itself. Stars rarely shine in isolation. They gather in bustling cosmic neighborhoods where gravity weaves them into intricate social structures. Picture the Pleiades, that glittering cluster visible to the naked eye, where newborn stars still cling to the remnants of their natal gas cloud. These open clusters are like stellar nurseries caught mid-transformation. their members young, hot, and full of restless energy. Over time, the gentle tug of galactic tides will pull them apart, scattering these sibling stars across the Milky Way like dandelion seeds in the wind. Yet for now, they remain a snapshot of stellar adolescence, their shared chemistry and motion telling astronomers the story of their collective birth. Contrast this with globular clusters, ancient celestial cities, where hundreds of thousands of stars crowd together in a gravitational embrace older than Earth itself. Omega Centauri, the Milky Way's largest globular cluster, resembles a swarm of fireflies frozen in time, its stars so densely packed that a planet orbiting one might see neighboring suns as bright as our full moon. What's astonishing is how these clusters have preserved their structure for nearly the age of the universe, their stars having burned through their fuel while remaining gravitationally loyal to each other. Their composition reads like a fossil record, almost devoid of heavy elements. They reveal a time before supernova had salted the cosmos with the ingredients for planets. The true power of studying these clusters lies in their comparative simplicity. Unlike the chaotic mix of ages and origins in the galactic field, cluster stars share a common birthplace and birthday. This makes them perfect laboratories for testing theories of stellar evolution. By observing how stars of identical age but different masses behave, seeing which have become red giants, which remain steady, and which have faded into stellar embers, astronomers refine their models like watchmakers studying identical gears. The cluster's motions also betray the Milky Way's hidden architecture. Globular clusters orbit in a vast halo, mapping out our galaxy's gravitational field like iron filings revealing the shape of a magnet. Perhaps most poetic is how these clusters mirror human social structures. Open clusters resemble vibrant college campuses, energetic but temporary gatherings where individuals eventually go their separate ways. Globular clusters, by contrast, are like ancient monasteries, preserving ways of stellar life that have otherwise vanished from the evolving galaxy. Both remind us that stars, much like people, are shaped by the communities they inhabit, whether fleeting or eternal, and that the universe writes its grandest stories not in solitary points of light, but in the dazzling choruses they form together. Galaxies are more than just random scatterings of stars. They're dynamic ecosystems where every sun plays a role in shaping the grand architecture of the cosmos. Picture the Milky Way's elegant spiral arms, those bright streaks studded with young blue stars. These aren't static decorations but stellar traffic jams, where density waves, like cosmic sound waves, compress gas and trigger new star formation. The hottest, most massive stars born here live fast and die young, their explosive deaths enriching the spiral arms with heavy elements that will seed future generations of stars and planets. Meanwhile, older red stars dominate the galactic bulge at the center, their collective gravity helping to maintain the galaxy's distinctive pinwheel shape over billions of years. Beyond the visible disk lies the galactic halo, a vast sphere of ancient globular clusters and wandering stars that tells a different story. These relics from the galaxy's violent youth orbit in all directions, their chaotic paths mapping out the Milky Way's hidden scaffolding of dark matter. The halo stars are cosmic historians. Their metal-poor composition reveals they formed when the universe was young, before countless supernovae had salted interstellar space with heavier elements. Yet even here, far from the bustling disk, stellar interactions continue to shape galactic evolution. When two stars pass close enough for gravity to bind them, they form binary systems that can eventually merge, sparking sudden stellar rebirths or even supernova that send shockwaves through the halo's sparse gas. The chemistry of galaxies depends entirely on their stellar populations. Every carbon atom in interstellar dust, every oxygen molecule in a nebula, was forged in a star's core and released through stellar winds or explosive deaths. This gradual enrichment transforms galaxies over time. Early galaxies shone mostly in the blue light of massive stars, while modern galaxies like ours glow with the warmer hues of longer-lived suns. The heaviest elements sink toward galactic centers, explaining why stars born today in the Milky Way's core contain more metals than those forming in the outskirts. This chemical gradient becomes a timeline, allowing astronomers to read a galaxy's history in the composition of its stars, much like geologists decipher Earth's past from rock layers. Perhaps the most profound stellar influence comes from the rarest but most powerful stars. Wolf-Rayet stars, for instance, blast out winds at millions of miles per hour, carving vast bubbles in surrounding gas that can trigger or suppress star formation across entire regions. When these titans finally explode as supernova, their shockwaves may push gas entirely out of a galaxy, starving it of the raw materials needed to make new stars. On the opposite end, red dwarfs, small, dim, and incredibly long-lived, act as galactic stabilizers, providing steady energy for trillions of years and potentially allowing life ample time to arise on orbiting planets. The interplay between stars and their galaxies creates a feedback loop that spans cosmic time. Young, metal-rich stars in spiral arms ensure continued star birth by churning and enriching nearby gas clouds. Old stars in halos and bulges maintain galactic structure through their collective gravity. Dying stars replenish the interstellar medium with elements for new solar systems. This cycle has transformed the first primitive galaxies, small, irregular blobs of gas and stars, into the majestic spirals and ellipticals we see today. And it continues still, with every newborn star subtly altering its galaxy's future, and every supernova scattering the seeds for worlds yet to form. The universe doesn't just contain galaxies, it grows them, one stellar generation at a time. Every star breathes, not in the way we do, but through vast, invisible exhalations that shape the cosmos over eons. Stellar winds, those relentless streams of charged particles, flow outward from stars in all directions, carrying fragments of their essence into the void. Our own sun sheds about 1.5 million tons of material every second through its solar wind, a whisper compared to the gales roaring from massive stars like Eta Carinae, where winds blast outward at over 4 million miles per hour. These aren't just particles, they're messages in a bottle containing atoms forged in the star's nuclear furnace, now set adrift to write new chapters in the universe's story. The solar wind might seem insignificant from our planetary perspective, but its influence is anything but. This constant outward pressure carves a protective bubble around our solar system called the heliosphere, shielding Earth from the brunt of galactic cosmic rays, high-energy particles that could strip away atmospheres or mutate DNA. Without this stellar breath, life as we know it might never have taken hold. Yet the sun's wind is a gentle breeze compared to the hurricanes unleashed by Wolf-Rayet stars, whose winds are so intense they sculpt surrounding gas into intricate shapes resembling celestial artwork. The Tarantula Nebula, for instance, glows with the fingerprints of these stellar mavericks, its filaments and cavities etched by winds powerful enough to vaporize entire planetary systems. What makes stellar winds truly transformative is their role as cosmic recyclers. Every atom of oxygen you inhale, every speck of silicon in a grain of sand, was likely carried across light years by these winds long before our solar system formed. When a star like Betelgeuse nears the end of its life, its winds grow heavier, laced with carbon, nitrogen, and oxygen elements that will one day become part of new stars, planets, or even living organisms. This isn't just recycling, it's the universe's way of passing wisdom between generations. The Orion Nebula's vibrant clouds, for example, shimmer with elements expelled by stars that died before Earth existed, now fueling the birth of stellar infants. The speed and composition of these winds also hold clues to a star's fate. A red giant's slow, dust-laden winds create the glowing shrouds of planetary nebulae, while the fierce gusts from blue supergiants can strip away their own outer layers, exposing their searing cores. Some stars, like those in binary systems, steal material from their companions only to blow it back into space through winds laced with newly forged elements. This constant give and take between stars and their surroundings builds up regions like the local bubble, a cavity in our galactic neighborhood where supernova and stellar winds have swept away gas, leaving behind a pocket of space that's unusually empty yet rich with the echoes of stellar activity. Perhaps the most profound realization is how these invisible currents connect us to the broader cosmos. The solar wind brushing past Voyager's instruments carries the same fundamental particles as the winds from stars 100 light-years away. They remind us that no star is truly isolated. Each contributes to a grand interstellar conversation, where atoms crafted in one furnace may eventually find their way into another. This endless cycle of expulsion and gathering, of destruction and creation, turns the galaxy into a living network where every stellar breath, no matter how faint, helps write the next sentence in the universe's unfolding story. Look up at the night sky and chances are you're seeing single stars, but the universe has a secret. Nearly half of all stars have companions, locked in gravitational dances that range from graceful waltzes to cosmic wrestling matches. These binary systems aren't just curiosities, they're celestial theaters where some of the universe's most spectacular dramas unfold. Take Sirius, the brightest star in our sky. What appears as one brilliant point is actually two stars, a main sequence star 23 times brighter than our Sun, and its faint white dwarf companion, packing a sun's worth of mass into an Earth-sized package. Their gravitational tango spans 50 years per orbit, a slow-motion ballet visible across interstellar distances. The physics of these stellar partnerships reads like a cosmic soap opera. In close binaries, one star can siphon material from its companion, creating accretion disks that glow with X-rays as stolen gas spirals inward. Systems like Algol, nicknamed the Demon Star for its eerie variability, show this theft in action. What was once the more massive star has become the smaller one, its outer layers stripped away by its greedy partner. This stolen material doesn't just vanish. It can trigger nova explosions when enough accumulates on a white dwarf's surface, briefly outshining entire galaxies. Some binaries take this drama to even greater extremes. When two massive stars orbit each other, their lives become intertwined in ways that single stars never experience. The more massive star ages faster, swelling into a red giant while its companion remains a blue main sequence star. Their gravitational embrace can grow so tight that the giant's outer layers engulf both stars, a phenomenon called common envelope evolution that either ejects the envelope into space or drags the stars closer together. The consequences are staggering. Some spiral inward until they collide, while others emerge as tight binaries where a neutron star or black hole orbits a normal star. Perhaps the most astonishing binary outcomes occur when both stars are massive enough to explode. The famous system HD 40804 consists of two blue supergiants orbiting each other every 61 days, both destined to die as supernova. If they survive each other's explosions, they might leave behind a binary black hole system, their invisible masses revealed only by their gravitational influence. Even more dramatic are neutron star binaries like the Hulse-Taylor pulsar, whose decaying orbit first proved Einstein's prediction of gravitational waves. When these ultra-dense remnants finally merge, they create kilonovae explosions that forge gold and platinum in quantities that dwarf Earth's entire reserves. What makes binaries so valuable to astronomers isn't just their spectacle, but the secrets they reveal. By measuring their orbits, we can weigh stars directly, something impossible for solitary stars. Their eclipses allow us to map stellar surfaces in incredible detail, while their interactions expose the inner workings of stellar evolution that single stars keep hidden. They're also cosmic timekeepers. The decay of binary neutron star orbits provides some of the strongest evidence for gravitational waves, ripples in spacetime first detected in 2015. Yet beyond their scientific value, binary systems remind us that relationships shape the universe at every scale. Whether it's two stars exchanging material, colliding in spectacular fireworks, or leaving behind dark remnants that continue their dance, these cosmic partnerships prove that even in the vast emptiness of space, nothing truly exists in isolation. The atoms in your body may have been forged in single stars, but they were likely scattered across the galaxy by the dynamic relationships of binaries, their gravitational dances stirring the cosmic pot that eventually led to planets, life, and you. Among the countless stars that shine with steady brilliance, some flicker like cosmic candles in the wind, variable stars that breathe in and out, their light waxing and waning over days, weeks, or even years. These celestial chameleons aren't just anomalies, they're astronomers' Rosetta Stones revealing secrets about stellar physics, galactic distances, and the very fabric of the universe. Take Delta Cephei, the prototype of Cepheid variables, a yellow supergiant that rhythmically swells and contracts like a giant's heartbeat. Every 5.4 days, its diameter changes by millions of kilometers, causing its brightness to nearly double before fading again. This predictable pulse isn't random, it's a precise cosmic metronome, with the star's pulsation period directly tied to its intrinsic luminosity. That relationship makes Cepheids cosmic yardsticks. When Henrietta Leavitt discovered this period luminosity connection in the early 20th century, it revolutionized astronomy. Suddenly, by measuring how long a Cepheid took to pulse and comparing it to how bright it appeared, scientists could calculate distances to far-off galaxies. Edwin Hubble used these stellar lighthouses to prove Andromeda wasn't just a nebula within our Milky Way, but an entirely separate galaxy, shattering humanity's perception of the universe's scale. Today, Cepheids remain vital for calibrating the cosmic distance ladder, helping pin down the expansion rate of the universe itself. Not all variable stars follow such orderly rhythms. Cataclysmic variables like the infamous SS Cygni spend most of their lives in quiet obscurity before suddenly erupting in violent outbursts. These binary systems consist of a white dwarf siphoning material from a companion star until the stolen gas accumulates to critical mass. Then boom, a thermonuclear explosion on the dwarf's surface can make the system 10,000 times brighter in hours. Such eruptions aren't just spectacular, they're stellar laboratories, showcasing how matter behaves under extreme pressures and temperatures impossible to replicate on Earth. Some variables tell even darker tales. RV Tauri stars, for instance, flicker unpredictably as they teeter on the edge of stellar stability, their outer layers convulsing in chaotic pulses. These aging giants are essentially cosmic hospice patients, shedding their skins in great dusty shrouds as they transition into planetary nebulae. Meanwhile, eclipsing binaries like Algol demonstrate variability through celestial choreography. Their light dips whenever one star passes in front of the other from our viewpoint, revealing precise details about their sizes, shapes, and atmospheres. The most extreme variables rewrite the rules entirely. Magneta's neutron stars with magnetic fields a quadrillion times stronger than Earth's can unleash gamma-ray flares so powerful they temporarily outshine the entire Milky Way. These outbursts stem from starquakes, where the neutron star's crust cracks under unimaginable magnetic stress, releasing energy equivalent to 1 billion atomic bombs. Even our own Sun is technically a variable star, its brightness fluctuating slightly over an 11-year cycle as magnetic activity waxes and wanes, a gentle reminder that variability is woven into the very nature of stellar existence. What makes these stars so invaluable is how their changes serve as diagnostics. A pulsating star's light curve, the graph of its brightness over time, acts like a stellar EKG, revealing internal structures and processes hidden beneath the surface. The way a star's spectrum shifts as it expands and contracts allows astronomers to map its atmospheric dynamics, much like meteorologists track weather systems. And in cataclysmic events, the sudden injection of energy can illuminate surrounding material, turning an otherwise invisible nebula or accretion disk into a fleeting cosmic flashlight. Variable stars remind us that the universe is anything but static. Their flickering lights carry messages across space and time about stellar life cycles, galactic architecture, and the fundamental laws governing matter and energy. From guiding ancient navigators to helping modern cosmologists measure the universe's expansion, these cosmic strobe lights continue to illuminate humanity's path to understanding the heavens. Every star holds the potential to become a solar system architect, crafting not just light and heat but entire worlds where chemistry might awaken into biology. The concept of a habitable zone, that Goldilocks region where temperatures allow liquid water to persist, transforms stars from mere points of light into potential life givers. Our own Sun cradles Earth perfectly within this zone, but astronomers have now identified over 50 exoplanets orbiting other stars where conditions might be just right for oceans to form. Take the TRAPPIST-1 system 39 light-years away, where 7 Earth-sized planets circle a tiny red dwarf. 3 of them orbit within the habitable zone, their surfaces potentially sculpted by tides from their star's gravity and warmed by its faint crimson glow. A star's personality dictates what kind of planets can thrive around it. Young, turbulent stars bombard their planets with violent flares, while calm, middle-aged stars like our Sun offer stable climates for billions of years. The metal content in a star's composition matters. 2 stars rich in elements heavier than hydrogen and helium tend to form rocky planets more readily. Kepler 186f, a planet discovered in 2014, orbits a star so iron-rich that astronomers speculate its crust might contain exotic metals rarely found on Earth. On the other end of the spectrum, planets around carbon-heavy stars could have surfaces littered with diamonds or graphite. Red dwarfs, the most common stars in the galaxy, present both promise and peril for habitability. Their faintness means their habitable zones are incredibly close, so close that planets there become tidally locked, with one side perpetually scorched and the other frozen. Yet these stars' longevity, some will shine for trillions of years, gives life an unimaginable time span to emerge and evolve. Meanwhile, massive blue stars, though dazzling, burn out too quickly for complex life to develop, their habitable zones lasting mere millions of years before expanding into oblivion. The search for Earth-like worlds has revealed astonishing diversity. Some planets orbit binary stars like Tatooine from Star Wars, experiencing double sunrises. Others, like Kepler 1625b, drift in the habitable zones of zombie stars, white dwarfs that have died and cooled. There's even evidence of rogue planets, untethered to any star, wandering the galaxy with subsurface oceans kept liquid by radioactive decay or gravitational squeezing. What makes these discoveries profound is how they rewrite the cosmic definition of home. Life might cling to moons around gas giants, like Jupiter's Europa, heated by tidal forces rather than starlight. Or it might thrive in the thick atmospheres of super-Earths, where airborne organisms could float indefinitely. Each star's unique properties, its size, temperature, and composition paint different possibilities for the worlds it nurtures. The ultimate legacy of stars isn't just the elements they forge or the light they emit, it's the stage they set for life's cosmic drama. Whether any of these exoplanets harbor biology remains unknown, but their very existence suggests the universe is generous with real estate where life could take root. Every twinkling dot in the night sky isn't just a star, it's a question, a possibility, a potential home for something wondrous we've yet to discover. Hidden within the glow of every star lies a cosmic time capsule, a record of elemental ingredients dating back to its birth. Astronomers decipher these clues through spectroscopy, splitting starlight into rainbows that reveal dark absorption lines like barcodes of chemistry. The oldest stars, found in the Milky Way's halo, display surprisingly simple barcodes, mostly hydrogen and helium, with barely a trace of heavier elements. These ancient relics, such as the 13.6 billion-year-old star He-1 52300901, are time machines to the universe's infancy, when the first stellar generations had yet to seed space with the carbon, oxygen, and iron we take for granted today. The chemical poverty of these primordial stars tells a dramatic story. Born from clouds of pure hydrogen and helium, the only elements available after the Big Bang, their compositions reflect a cosmos before supernova enriched interstellar space. The star SMSS J0313088062, for instance, contains less than 1/1,000,000th the iron of our Sun. Yet nestled within its spectrum, astronomers found a single weak line of calcium, a ghostly signature hinting at just one ancient supernova whose explosion polluted this star's natal cloud. These subtle traces allow scientists to reconstruct the lives and deaths of the very first stars, giants hundreds of times more massive than our Sun that lived fast and died violently. Modern stellar archaeology goes beyond chemistry to track galactic history through motion. Stars born together in clusters share not just composition but orbital dynamics, like siblings with the same accent and stride. By mapping the paths of halo stars with telescopes like Gaia, astronomers have uncovered stellar streams, elongated groups of stars moving in unison, that are the shredded remains of dwarf galaxies swallowed by the Milky Way billions of years ago. The Sagittarius Stream, a ribbon of stars arching across our galaxy, marks where a satellite galaxy was torn apart by tidal forces, its stars now serving as breadcrumbs leading back to this cosmic cannibalism. Perhaps the most astonishing revelation from stellar fossils is how they've rewritten the timeline of cosmic enrichment. The oldest stars lack elements like europium and gold, which require rare neutron star collisions to form. Their absence suggests these dramatic events took hundreds of millions of years to become common. Yet some stars, like the peculiar BD plus 44493, sport unexpected lithium abundances, a puzzle pointing to processes in the early universe we're still unraveling. Each anomaly is a clue helping astronomers piece together how the sterile hydrogen-helium soup of the young cosmos transformed into the chemically rich universe we inhabit today. This celestial detective work doesn't just illuminate the past, it reshapes our future. By understanding how early stars and galaxies formed, we refine models predicting how our Milky Way will collide with Andromeda, or how dark matter's pull sculpts stellar orbits. The next generation of telescopes, like the Vera Rubin Observatory, will discover millions more fossil stars, turning individual data points into a statistical symphony of cosmic evolution. Every faint, ancient sun we analyze is a verse in the universe's autobiography, written not in ink but in the language of elements and orbits, a story we're only beginning to translate. Our sun doesn't just light up the sky, it's the silent architect of every sunrise, every gust of wind, and every blade of grass that's ever grown. 4.5 billion years ago, its birth ignited the gravitational dance that sculpted Earth from swirling dust and gas. Without the sun's steady pull, our planet would never have found its orbit in the habitable zone, that narrow ribbon of space where water stays liquid and chemistry can blossom into biology. But the sun's influence goes far beyond mere warmth. Every raindrop that's ever fallen owes its journey to solar energy driving the water cycle, evaporating oceans and lifting vapor into clouds. Every breath you take contains oxygen produced by ancient sunlight energy captured by plants and algae through photosynthesis, a process that's been fueling Earth's biosphere for 3 billion years. Solar activity weaves an invisible thread through human history. The Maunder Minimum, a period of unusually quiet sunspots in the 17th century, coincided with the Little Ice Age frost fairs on the Thames and crop failures that reshaped societies. Conversely, the Carrington event of 1859, the most powerful solar storm ever recorded, set telegraph wires ablaze with induced currents and painted auroras so bright they woke gold miners in California, mistaking the glow for dawn. Today, a similar storm could cripple power grids and satellites, a reminder of how deeply tethered our technology is to the sun's whims. Even the northern lights, those ethereal curtains of color, are solar graffiti particles from the solar wind colliding with Earth's magnetic field, painting the sky with the sun's signature. Yet the sun's constancy is an illusion. In 5 billion years, its core will exhaust its hydrogen fuel, triggering a transformation that will redefine our solar system. As it swells into a red giant, its outer layers will engulf Mercury and Venus, while Earth's oceans boil away and its crust melts under unbearable heat. Long before that, in just 1 billion years, the sun's gradual brightening will evaporate Earth's water vapor, triggering a runaway greenhouse effect that mirrors Venus today. These aren't abstract predictions, they're chapters in a story already written by stellar physics, a countdown clock set at the sun's birth. Understanding our star isn't just about astronomy, it's about gratitude. The sun's stable middle age, a rarity among stars, gave evolution the time it needed to craft complex life. Its Goldilocks luminosity, neither too fierce nor too faint, kept Earth's climate balanced through eons. Even its tantrums, those solar flares and coronal mass ejections, may have played a role in sparking life by delivering energetic particles to primordial soups. As we search for life around other stars, the sun stands as both a blueprint and a cautionary tale, proof of how a star can nurture a living world, and a reminder that no cosmic harbor lasts forever. The aftermath of a supernova is anything but empty space. It's a celestial construction site where the shattered remains of a star become the raw materials for cosmic rebirth. Picture the Crab Nebula, a tangled web of glowing filaments stretching 11 light-years across, its delicate tendrils energized by the relentless spin of a pulsar at its heart. This isn't just debris, it's a stellar phoenix rising from the ashes of an explosion witnessed by Chinese astronomers in the year 1054. Every twist of gas in this remnant carries elements forged in the star's final moments: oxygen, neon, iron, now flung outward at 5 million kilometers per hour to seed future generations of stars. What makes these remnants so fascinating is how they evolve. In their youth, they're dominated by the shockwave from the explosion, a spherical tsunami of gas plowing into interstellar space. Over centuries, that shockwave sculpts the surrounding material into intricate structures, like the bubble-like veil of Cygnus Loop or the jagged edges of Cassiopeia A. The hottest regions glow in X-rays, while cooler filaments radiate visible light, creating otherworldly landscapes visible through telescopes. As the remnant ages, over tens of thousands of years, it gradually disperses, its atoms blending with the interstellar medium like cream swirling into coffee. The chemistry happening inside these remnants is where the real magic lies. The violent collisions between ejected material and surrounding gas create conditions ripe for molecule formation, everything from simple carbon monoxide to complex organic compounds. The famous supernova remnant W44, for instance, contains enough alcohol molecules to fill Earth's oceans trillions of times over. While you wouldn't want to drink this space cocktail, its existence proves how stellar deaths can set the stage for prebiotic chemistry. Even more remarkably, remnants act as particle accelerators, their shockwaves boosting cosmic rays to near-light speed subatomic bullets that may have influenced the mutation rates of early life on Earth. Perhaps no remnant better illustrates this cycle of destruction and creation than the Vela supernova remnant. Spanning 200 light-years, its delicate filaments resemble a ghostly jellyfish drifting through space. At its center lies the Vela pulsar, spinning 11 times per second and powering the nebula's glow. But look closer, and you'll find something astonishing. The remnant shockwave is colliding with a nearby molecular cloud, compressing the gas so intensely that new stars are beginning to ignite. It's a cosmic demonstration of how death gives birth, the ashes of one star triggering the birth of others, complete with planets that may one day harbor life. These remnants also serve as cosmic time capsules. By measuring how quickly they expand, astronomers can work backward to determine exactly when the original supernova occurred. The Kepler supernova remnant, for example, was long thought to be from a star observed in 1604, but modern measurements show its explosion actually happened 20,000 years earlier. The light simply took millennia to reach Earth. Others, like the mysterious Hoenga remnant discovered in 2021, challenge our understanding of how often massive stars explode, revealing gaps in our galactic supernova records. The ultimate legacy of supernova remnants isn't just in the stars they'll help build, but in how they've already shaped us. The iron in your blood, the calcium in your bones, these atoms were likely forged in multiple supernovae before being incorporated into our solar system's birth cloud. Every remnant we see is a chapter in that story, a temporary monument to stellar sacrifice that will one day fade into the galactic background, its elements reborn in new forms. They remind us that the universe wastes nothing, not even a star's dying breath, and that every ending is laced with the promise of beginnings yet to come. If you could see the Milky Way not just as a swirl of stars but as a gravitational blueprint, an astonishing truth would emerge. The stars we observe are mere breadcrumbs tracing the outline of something far larger and invisible. Dark matter, this enigmatic cosmic sculptor, doesn't shine, absorb, or reflect light, yet its gravitational grip orchestrates the motion of every star in our galaxy. Take the outer stars of the Milky Way. For instance, they orbit so fast that without some unseen mass anchoring them, they'd fling into intergalactic space. The math is clear. The visible matter in galaxies accounts for barely 15% of the gravity needed to hold them together. The rest, an invisible scaffold of dark matter, its presence felt only through the way it bends the paths of stars like an unseen hand guiding a spinning top. This cosmic shadow doesn't just lurk in galaxies, it weaves the universe's largest structures. When astronomers map galaxy clusters like the Bullet Cluster, they find a startling disconnect. The visible gas, heated to millions of degrees in collisions between galaxies, lags behind the bulk of the mass revealed by gravitational lensing. It's as if two cosmic ghosts pass through one another, their dark matter halos slipping past unscathed while ordinary matter piled up like traffic in a crash. These observations suggest dark matter isn't just an afterthought, it's the universe's backbone, the framework upon which galaxies assemble like dew on a spider's web. But how do we study something we can't see? Stellar motions are the key. Just as you might infer the shape of a hidden magnet by watching iron filings align, astronomers reconstruct dark matter's distribution by tracking how stars and gas clouds move. The Andromeda Galaxy, for example, rotates so uniformly that its stars must be embedded in a vast, diffuse halo of dark matter, a halo stretching far beyond the galaxy's visible edge. Even more telling are ultra-faint dwarf galaxies like Segway 1, where stars are so few and far between that dark matter outweighs visible matter by 10,000 to 1. These cosmic minnows are essentially dark matter detectors, their stars tracing the contours of an otherwise invisible sea. The hunt for dark matter's identity has sparked some of astronomy's most creative experiments. Deep underground, detectors like LUX Zeppelin wait for hypothetical WIMP weakly interacting massive particles to bump into atomic nuclei. In space, the Fermi Gamma Ray Telescope scans for anomalous light that might betray dark matter particles annihilating one another. Yet despite decades of searching, dark matter remains elusive, refusing to reveal itself beyond its gravitational shadow play. Some theorists have even proposed tweaking the laws of gravity itself, suggesting that what we call dark matter might instead be a flaw in our understanding of how gravity works on galactic scales, a hypothesis known as MUND, or modified Newtonian dynamics. What's undeniable is dark matter's starring role in cosmic history. Without it, the slight density fluctuations in the early universe wouldn't have amplified enough to birth galaxies. The first stars might never have ignited, and the cosmic web, that vast filamentary network threading the cosmos, would lack its scaffolding. Dark matter isn't just a mystery, it's the unseen architect of every shining structure in the night sky. As we peer deeper into the motions of stars and galaxies, we're not just mapping the universe we see, we're deciphering the handwriting of an invisible cosmos, one stellar orbit at a time. The universe is growing emptier by the second, not with a bang, but with a slow, inexorable stretching of space itself. Every galaxy beyond our local group is being carried away by this expansion, their light stretched into invisibility as cosmic distances become too vast even for light to bridge. Imagine a night sky where all but a handful of the closest galaxies have vanished, their stars redshifting into oblivion like ships disappearing over the horizon. The Andromeda Galaxy, our nearest major neighbor, will eventually merge with the Milky Way in a spectacular collision, but after that, there will be no new galaxies to meet. The rest will have receded beyond an unreachable horizon, leaving our merged galaxy island adrift in an ever-darkening void. This cosmic isolation won't just affect galaxies, it will strangle the birth of new stars. Star formation thrives on dense molecular clouds, but as the universe expands, these gas reservoirs are being diluted like ink dropped into an ever-growing ocean. In about 100 billion years, the last gas clouds will either collapse into stars or be blown apart by stellar winds, leaving no raw material for new generations. The universe's star-making factories will shutter one by one, their lights flickering out as the era of starbirth draws to a close. Already, we see this slow down in action. The peak of star formation passed 10 billion years ago, and today's universe produces stars at just a fraction of that rate. Yet, even as the cosmos grows darker, the remaining stars will persist in astonishing variety. Red dwarfs, those frugal stellar misers, will continue burning for trillions of years, their faint glow outlasting all other stars. White dwarfs, the cooling embers of sun-like stars, will dominate the galaxy's stellar population, their heat slowly leaking into space over timescales longer than the current age of the universe. And neutron stars, these ultra-dense remnants, will keep spinning down, their magnetic fields gradually weakening until they become nearly invisible silent tombstones marking where massive stars once blazed. The final chapters of stellar evolution will unfold in near total darkness, as protons, the building blocks of atoms, begin decaying in 10 to the 34th power years. Even white dwarfs and neutron stars will evaporate into subatomic particles. Black holes will become the last stars standing, slowly losing mass through Hawking radiation until they too dissolve in a faint burst of particles. The universe will enter the so-called dark era, where no stars shine, no planets orbit, and no light pierces the endless cold. But this grim fate is unimaginably distant, a future so far removed from our present that it might as well be science fiction. For now, the universe remains vibrantly alive with stellar activity. New stars ignite in dusty nurseries, supernovas seed the cosmos with heavy elements, and binary systems dance their gravitational waltzes. Every second, stars across the universe are being born, evolving, and dying in a grand cycle that has persisted for over 13 billion years. What's remarkable is how this ongoing stellar drama continues to shape the universe's trajectory. The heat and light from stars ionize interstellar gas, influencing how galaxies evolve. The heavy elements they forge become the building blocks for planets and, potentially, life. Even as the universe expands toward darkness, the stars of today are writing the next chapter in cosmic history, one where their legacy persists in the chemistry of space, the architecture of galaxies, and perhaps even in the biology of distant worlds. Their light may fade in the end, but their influence echoes across eternity. Long before science unraveled the true nature of stars, they burned brightly in the human imagination as characters in an endless celestial drama. The ancient Greeks saw Orion not as a random scattering of stars, but as a mighty hunter forever chasing the Pleiades across the sky, his story etched in glittering constellations. Meanwhile, halfway across the world, the Maya visualized the same stars as a cosmic turtle, the portal to the underworld in their creation myth. These celestial stories weren't just entertainment. They were humanity's first attempts to make sense of the cosmos, turning cold points of light into a familiar tapestry of gods, animals, and heroes. The Big Dipper, that unmistakable asterism in Ursa Major, shows how differently cultures interpreted the same stars. To the Norse, it was Odin's wagon, carrying the god of wisdom across the heavens. Native Algonquin tribes saw it as a great bear pursued by hunters, while ancient Chinese astronomers recognized it as the Northern Dipper, its orientation marking the changing seasons. What's remarkable is how these myths often served practical purposes. Polynesian navigators used star stories as mnemonic devices, memorizing constellations to guide their voyages across thousands of miles of open ocean. The Maori of New Zealand timed their planting seasons by the helical rising of Matariki, the Pleiades, whose appearance signaled the start of their new year. Some stellar myths reveal surprising astronomical insights hidden in metaphor. The Aboriginal story of the emu in the sky doesn't focus on bright stars but on the dark patches of the Milky Way, an astonishing recognition of interstellar dust clouds millennia before telescopes confirmed their existence. Similarly, the Babylonian Venus tablets recorded the planet's movements with such precision that modern astronomers used them to calculate changes in Earth's rotation over 3,000 years. These cultures were doing more than telling stories. They were encoding observations that would take Western science centuries to rediscover. Even star names carry echoes of ancient worldviews. Sirius, the brightest star in our sky, derives its name from the Greek for scorching, a nod to its appearance during the hottest days of summer. But look deeper and you'll find the star was known as Sopdet to the Egyptians. Its annual return heralded the Nile's life-giving floods. The red giant Antares gets its name from Anti-Ares, meaning rival of Mars for its similar hue, but to ancient Persians it was Sattvis, one of 4 royal stars marking the seasons. Each name is a cultural fingerprint, revealing how different civilizations projected their values onto the cosmos. Modern astronomy may have replaced myths with physics, but the legacy of these stories endures. The International Astronomical Union's official constellation boundaries still follow the mythological figures mapped by Ptolemy in the 2nd century. Spacecraft like Apollo and Orion carry the names of mythological heroes into the heavens, and when astronomers search for exoplanets today, they often use names proposed by the public, continuing the ancient tradition of connecting human stories to the stars. The night sky was humanity's first storybook, and though we now understand stars as nuclear furnaces, they still spark that same primal wonder. When you look up at Orion tonight, you're seeing not just a stellar formation, but the accumulated dreams of countless generations who found meaning in the dark. Modern telescopes have transformed the night sky from a static canvas into a living, evolving portrait of cosmic history. The Hubble Space Telescope, launched in 1990, became our first long-term eye in the heavens. Free from Earth's blurring atmosphere, it captured details in stellar nurseries and dying stars that ground-based telescopes could only dream of. One of its most breathtaking images, the Pillars of Creation, revealed towering columns of gas in the Eagle Nebula where new stars were being born. These weren't just pretty pictures. They were scientific revelations, showing how radiation from nearby massive stars sculpts star-forming regions like a cosmic sandblaster. Hubble's observations of Cepheid variable stars also helped pin down the universe's expansion rate with unprecedented precision, settling a decades-long debate among astronomers. Then came the James Webb Space Telescope, Hubble's infrared successor, which peered through cosmic dust clouds like never before. Where Hubble saw opaque curtains, Webb revealed intricate stellar nurseries where protostars flicker to life. Its early images of the Carina Nebula exposed bubbles and jets carved by newborn stars, while its spectra of exoplanet atmospheres detected water vapor and potential biosignatures around distant worlds. Webb's greatest triumph might be spotting galaxies so ancient they shouldn't exist, stellar cities that formed when the universe was less than 300 million years old, challenging our models of cosmic dawn. Ground-based observatories have kept pace with these space telescopes, using adaptive optics to counteract atmospheric distortion. The Very Large Telescope in Chile, for instance, captured a star orbiting the Milky Way's central black hole in real time, a 20-year time-lapse proving Einstein's theories in action. Meanwhile, radio telescopes like ALMA mapped planet-forming disks around young stars with astonishing detail, revealing gaps where infant worlds are clearing their orbits. Even amateur telescopes now contribute to discoveries, with citizen scientists spotting supernova and tracking variable stars through projects like the American Association of Variable Star Observers. The next generation of telescopes promises to peel back even more cosmic layers. The Nancy Grace Roman Space Telescope will survey billions of galaxies to study dark energy's influence on cosmic expansion. The Extremely Large Telescope, with its 39-meter mirror, will directly image exoplanets and analyze their atmospheres for signs of life. And the Laser Interferometer Space Antenna will detect gravitational waves from merging supermassive black holes, listening to the universe's hidden symphony. What's exhilarating is how each technological leap doesn't just answer old questions, it reveals new mysteries. Webb's early galaxies suggest we're missing pieces in our understanding of star formation in the infant universe. Hubble's deep fields showed galaxies evolving in unexpected ways. Every time we build a better window to the cosmos, the universe reminds us how much we have yet to learn. These telescopes aren't just tools, they're time machines, letting us witness stellar births from billions of years ago while hinting at discoveries still waiting in the darkness. Before the Milky Way's spiral arms took shape, before galaxies even existed, the first generation of stars ignited in the cosmic dark, colossal behemoths unlike anything shining today. These population 3 stars were the universe's pioneers, born from clouds of pure hydrogen and helium left by the Big Bang. Without heavier elements to cool their cores or regulate their growth, they ballooned to masses hundreds of times that of our Sun, burning at temperatures so extreme their light was tinted blue-violet, like a welder's torch piercing the primordial gloom. Their lives were spectacularly brief, some surviving just a few million years before exploding in titanic supernova that would forever alter the chemistry of the cosmos. The quest to find evidence of these stellar ancestors is like searching for dinosaur footprints in stone. Their bodies are long gone, but traces remain. Astronomers scour the spectra of the universe's oldest known stars and gas clouds, hunting for elemental fingerprints that only population 3 supernova could leave behind. Imagine finding a fossil with no calcium in its bones. That's what scientists look for in stars like He 132700036, a relic star in our galactic halo with almost no heavy elements. Its composition suggests it formed from gas polluted by just 1 or 2 of those early supernovae, carrying the chemical equivalent of a cosmic birth certificate. The challenge is that these first stars didn't just explode. They annihilated themselves in pair instability supernova, events so violent they left no neutron star or black hole behind. Entire stars vanished in bursts of energy that outshone galaxies, forging the first carbon, oxygen, and silicon atoms but leaving little debris to study. Yet their legacy is everywhere. The iron in your blood, the gold in your jewelry, even the iodine in your thyroid were all forged in later generations of stars that built upon those primordial explosions. Recent breakthroughs hint we're closing in on population 3's ghostly signatures. The James Webb Space Telescope has spotted distant galaxies glowing with unusual patterns of helium and hydrogen, possibly illuminated by the death throes of these first stars. Meanwhile, simulations suggest some population 3 stars might have lived on as dark matter-powered objects called dark stars, their faint infrared glow detectable in Webb's deepest images. What makes this hunt so thrilling isn't just filling a gap in cosmic history, it's about understanding how chaos birthed order. Those first supernovae didn't just create elements, they triggered shock waves that compressed nearby gas, accelerating the formation of later stellar generations and the galaxies they call home. Finding population 3 would be like uncovering the Rosetta Stone of cosmic evolution, revealing how a featureless early universe transformed into the intricate tapestry we see today. Their light may be gone, but their echoes still shape everything we are. In the vast cosmic dance of stars, collisions are the rarest and most violent waltzes imaginable, events where celestial giants meet in catastrophic embraces that rewrite their destinies. Picture 2 stars, each 1,000,000 kilometers wide, drawn together by gravity until their outer layers shred into spiraling tidal tails, their cores merging in a fireball hotter than a supernova. While such encounters occur only once every 10,000 years in our galaxy, their aftermaths are nothing short of spectacular. Take the red nova V1300 Scorpii, which flared to prominence in 2008, a once faint star suddenly outshining its entire stellar neighborhood. Astronomers later confirmed this was no ordinary explosion but the violent merger of two binary stars, their combined mass triggering a runaway nuclear reaction that painted the cosmos with rare isotopes like radioactive titanium. These collisions don't just create dazzling light shows, they forge entirely new classes of objects. In globular clusters, where stars pack together 1,000,000 times more densely than near our Sun, stellar smash-ups can produce blue straggler stars that appear bizarrely young and hot compared to their ancient surroundings. These cosmic Frankenstein's monsters, like the blue stragglers in the cluster M30, defy normal stellar evolution by stealing mass from neighbors or outright merging, effectively hitting the reset button on their lifespans. Some collisions in these crowded stellar cities even create Thorne-Zitkow objects, hypothetical hybrid stars where a neutron star orbits inside a red giant's envelope, a celestial matryoshka doll with unimaginable density at its heart. The densest regions of galaxies, like the area surrounding supermassive black holes, become stellar demolition derbies. Near Sagittarius, a star, our galaxy's central black hole, stars whip around at thousands of kilometers per second, so fast that near misses can strip entire atmospheres or fling planets into interstellar space. Occasionally, two stars collide head-on, their combined mass igniting into a short-lived supermassive star that briefly outshines the rest of the galactic core. These events may explain mysterious flares observed in distant active galaxies, where sudden bursts of ultraviolet light suggest stars merging like moths drawn too close to a flame. Perhaps the most consequential collisions involve neutron stars. When these ultra-dense remnants spiral together, their merger creates kilinovae explosions that forge gold, platinum, and other heavy elements in quantities dwarfing Earth's entire reserves. The gravitational waves from one such merger, detected in 2017, carried signatures of these precious metals being synthesized in real time. These rare events solve a cosmic mystery: why the universe contains more gold than standard supernova could produce alone. Every wedding ring on Earth may contain atoms born in neutron star collisions that occurred billions of years before our solar system formed. While stellar collisions seem like freak accidents, they've shaped the universe in profound ways. In the early cosmos, when galaxies were smaller and stars packed tighter, mergers may have been 10 times more common, explaining why some ancient stars show unusual chemical abundances. Today, their shockwaves can compress nearby gas clouds, triggering fresh rounds of star birth like cosmic dominoes. The Butterfly Cluster, a stellar nursery near the galactic center, shows evidence of such triggered formation, its youngest stars arranged in patterns suggesting they were born from the debris of older stars that collided eons ago. These violent encounters remind us that the universe is far from static. Just as Earth's history has been punctuated by asteroid impacts and continental collisions, the stellar realm experiences its own epochal crashes, rare but transformative moments where chance encounters rewrite cosmic chemistry and redistribute matter on galactic scales. Every time we observe an unusual star with odd motions or unexpected brightness, we might be seeing the aftermath of a celestial collision, a cosmic car crash whose echoes will reverberate for millennia. Every breath you take is a conversation with the star's oxygen atoms forged in the fiery hearts of red giants, now cycling through your lungs in an endless cosmic exchange. The periodic table isn't just a chemistry chart, it's a stellar obituary, each element a tombstone marking the death of a star that sacrificed itself to enrich the universe. Carbon, the backbone of life, was created in the gentle fusion of middleweight stars like our Sun. The iron in your blood that required something far more violent, a supernova's apocalyptic fury, where atomic nuclei were bombarded with neutrons in seconds, forming elements so heavy they could only exist in the heart of a dying star's collapse. Stellar spectroscopy, the art of decoding starlight, reveals this elemental tapestry in breathtaking detail. When astronomers train their telescopes on a star, they're not just measuring brightness, they're reading chemical barcodes. Dark absorption lines in a star's spectrum act like fingerprints, each corresponding to specific elements in its outer layers. The Sun's spectrum, for instance, betrays traces of 67 elements, from hydrogen and helium to rarities like gold and uranium. But compare that to HD 140283, a nearby ancient star, and you'll find its metal content is 200 times poorer, a time capsule from an era before supernova had salted the cosmos with heavy elements. The universe's elemental inventory changes over time like a slowly evolving recipe. In the beginning, only hydrogen and helium existed, primordial ingredients from the Big Bang's nuclear furnace. Then came population 3 stars, those first massive giants, whose supernova seeded space with carbon, oxygen, and nitrogen. Later generations of stars built upon this foundation, with red giants contributing elements like strontium and barium through slow neutron capture, while supernova and neutron star collisions forged gold, platinum, and uranium in rapid neutron capture processes. This staggered production explains why oxygen is common, produced abundantly in many stars, while gold remains rare, requiring the most extreme cosmic events. Some stellar chemical signatures defy expectations. Piazzi-Bilski's star, for example, exhibits bizarre lines corresponding to short-lived radioactive elements like promethium elements that should have decayed billions of years ago. One theory suggests it's accreting material from a nearby neutron star, a cosmic siphon dripping exotic isotopes into its atmosphere. Then there's the curious case of carbon stars, aging suns that have dredged up carbon from their cores, turning their atmospheres into sooty factories producing complex organic molecules. These stars are essentially cosmic chemists, brewing compounds like benzene and cyanide in their outer layers, precursors to the chemistry that might seed life elsewhere. What's humbling is how these stellar factories connect to our daily lives. The neon in storefront signs, forged in the cores of massive stars and scattered by supernova. The calcium in your bones, synthesized in the last gasps of a white dwarf's thermonuclear explosion. Even the uranium powering nuclear reactors owes its existence to neutron star mergers, events so rare that a single teaspoon of uranium represents the debris from thousands of such collisions across galactic history. This grand recycling program stretches across space and time. The carbon dioxide you exhale might one day be incorporated into a distant molecular cloud, then compressed into a new star system's planets. Your jewelry contains gold atoms that survived multiple supernova, neutron star collisions, and billions of years adrift in space before Earth even formed. Stars don't just make elements, they weave them into the fabric of galaxies, planets, and life itself, turning the cosmos into an interconnected web where every atom has a lineage stretching back to the first starlight. A star's lifespan is written in its mass, a cosmic contract signed at birth that dictates whether it will blaze through existence like a firework or endure as a slow-burning ember across eons. The most massive stars, those celestial behemoths tipping the scales at over 100 solar masses, live lives of extravagant intensity. Take Eta Carinii, a hypergiant so unstable it convulses with eruptions, ejecting entire solar systems worth of material into space. Such stars burn through their hydrogen fuel in mere millions of years, a cosmic eye blink compared to our Sun's 10 billion-year journey. Their brilliance comes at a cost. Like prodigies burning too bright, they exhaust themselves young, collapsing into spectacular supernova or even more exotic remnants like black holes. At the opposite extreme are red dwarfs, the universe's frugal hermits. Stars like Proxima Centauri, weighing just 12% of our Sun's mass, sip their hydrogen reserves so slowly that their projected lifespans stretch into trillions of years. To put that into perspective, the entire universe is only 13.8 billion years old. These dim crimson stars will still be shining long after every other star type has faded, their steady glow outlasting galaxies themselves. Their longevity makes them fascinating candidates for hosting life, if their planets can withstand the frequent solar flares that characterize their turbulent youth. Between these extremes lies a spectrum of stellar lifetimes dictated by simple physics. A star's core temperature rises with mass, accelerating nuclear fusion exponentially. Double a star's mass and it burns through fuel not twice as fast but up to 10 times faster. This explains why Sirius, twice our Sun's mass, will live only 1/10 as long despite having twice the fuel. Medium-sized stars like our Sun strike a balance. Their 9 to 10 billion year main sequence lifespans provide the stability needed for planetary evolution and potentially the emergence of life. The diversity of stellar lifespans creates a cosmic conveyor belt of element production. Massive stars are the universe's sprinting alchemists, rapidly synthesizing heavy elements and scattering them through supernova to enrich future star-forming regions. Meanwhile, red dwarfs act as galactic anchors, preserving primordial hydrogen across timescales that dwarf civilizations. This interplay ensures that at any point in cosmic history, stars of varying ages contribute to galactic ecosystems, whether by forging new elements, triggering star formation through their deaths, or providing steady energy for potential life. Astronomers use stellar lifespans as clocks to date cosmic structures. Globular clusters, those ancient stellar cities orbiting our galaxy, contain stars barely more massive than the Sun, their dimming light revealing ages approaching 13 billion years. The absence of massive stars in these clusters confirms their extreme age, as all such short-lived stars vanished eons ago. Similarly, when we observe distant galaxies dominated by blue supergiants, we're seeing snapshots of their youth, stellar metropolises still in their star-forming frenzy before the inevitable demographic shift toward longer-lived stars. Looking ahead, stellar lifespans sketch the universe's future. As the last massive stars die off in another 100 billion years, the cosmos will grow progressively redder and dimmer, dominated by the persistent glow of red dwarfs. The era of starbirth will end as gas supplies dwindle, leaving these miniature suns as the sole sources of light in an increasingly dark universe. Their extraordinary endurance means they'll be the final witnesses to cosmic evolution, their patient fusion sustaining islands of warmth in the expanding void long after all other stellar lights have gone out. Consider the humble red dwarf, the most common star in our galaxy, outnumbering stars like our Sun 10 to 1. These diminutive crimson embers burn so faintly that a planet would need to orbit startlingly close to bask in their warmth, often closer than Mercury hugs our Sun. But this proximity comes at a cost: tidal locking. One side of the planet perpetually faces its star, baking under eternal daylight, while the other side freezes in permanent darkness, a scenario hardly conducive to life as we know it. Worse still are the flares. A typical red dwarf can unleash eruptions 10,000 times more powerful than anything our Sun produces, bombarding nearby planets with sterilizing radiation. Proxima Centauri b, the closest known exoplanet to Earth, endures such violent stellar tantrums that its atmosphere may have been stripped away long ago, leaving a desiccated rock where oceans once might have pooled. At the opposite extreme blaze the massive O-type stars, celestial titans that shine with the brilliance of a million suns. Their habitable zones stretch staggeringly far, but these stars are cosmic mayflies, surviving just a few million years before detonating as supernova. Imagine a star system like HD 93129A, where planets form amidst swirling protoplanetary disks. Before these worlds can even cool from their molten births, their parent star explodes, scouring any potential biospheres with gamma rays and shockwaves. The very ultraviolet radiation that makes these stars so luminous also shreds complex molecules in their vicinity, turning their planetary nurseries into chemical dead zones long before biology could gain a foothold. Between these extremes lies the sweet spot stars like our Sun, classified as G-type main sequence stars. Their golden light bathes planets in steady warmth for billions of years, allowing for the gradual evolution of complex chemistry. The Sun's habitable zone, extending roughly from Venus' orbit to Mars, provides just enough thermal variation for liquid water to persist across geological timescales. Crucially, these stars avoid the violent mood swings of red dwarfs while offering lifespans long enough for multicellular life to emerge. Earth required nearly 4 billion years of stable conditions to evolve intelligent life, a time span only possible around stars with similarly patient fusion engines. The concept of stellar Goldilocks zones reshapes how we search for extraterrestrial life. Kepler's census of exoplanets revealed thousands of worlds orbiting diverse stars, but only a fraction circle stars with the right mix of stability and longevity. Take Kepler 452b, a rocky world dubbed Earth's cousin for its Sun-like star and orbit within the habitable zone. While its star is slightly older and brighter than ours, it represents the kind of stellar environment where life's delicate experiments might have time to unfold. Contrast this with TRAPPIST-1's 7 planets all crammed into orbits smaller than Mercury's around their erratic red dwarf host, where frequent flares and gravitational stresses create environments more akin to pressure cookers than cradles of life. Yet nature always surprises us. Some theorists speculate that moons orbiting gas giants in red dwarf systems might avoid tidal locking by interacting with their planet's gravity, creating day-night cycles through orbital resonances. Others suggest that the thick atmospheres of super-Earths could redistribute heat from permanent day sides to night sides, creating narrow bands of temperate real estate. Even around massive stars, there's a fleeting chance for life on rogue planets ejected from their system's worlds warmed by geothermal activity or insulating hydrogen atmospheres, drifting freely between the stars. Ultimately, stellar Goldilocks zones remind us that habitability isn't just about finding Earth twins. It's about understanding how a star's personality shapes the possibilities for life around it. As we discover more exoplanets, we're learning that the universe writes its recipes for life in diverse stellar kitchens. Some ovens burn too hot and fast, others too cold and erratic. But around certain steady, middle-aged stars, the conditions might just be right for the alchemy of life to simmer patiently toward complexity. Interstellar travel isn't just science fiction, it's a challenge written in the language of stars themselves. Proxima Centauri b, the closest known exoplanet, orbits a red dwarf just 4.2 light-years away. But that just is deceptive. At the speed of New Horizons, our fastest spacecraft, the journey would take 75,000 years longer than human civilization has existed. This crimson sun, though nearby, presents harsh realities. Its habitable zone is 20 times closer than Earth's, bathing any planet in flares capable of stripping atmospheres. Yet, if shielded by a magnetic field or thick atmosphere, Proxima b could harbor liquid water in perpetual twilight zones, where one side always faces the star and the other freezes in eternal night. Venture farther and brighter targets emerge. Sirius, the sky's most luminous star, blazes twice as hot as our Sun with a white dwarf companion, a binary system where any habitable worlds would face extreme tides and radiation. Vega, another nearby beacon, spins so fast it bulges at its equator, distorting potential planetary orbits. These stars aren't just destinations, they're laboratories for testing human ingenuity. Imagine a civilization harnessing Vega's intense ultraviolet light for energy, or mining the dense carbon-rich remnants around Sirius B, where a teaspoon of material outweighs an elephant. The scale of these journeys redefines ambition. Even with theoretical propulsion like light sails pushed by lasers, reaching Alpha Centauri would take decades. Breakthrough Starshot's vision of gram-scale probes traveling at 20% light speed still requires overcoming cosmic dust impacts and communication across light years. Yet, the stars offer more than survival, they promise transformation. Tau Ceti, a Sun-like star 12 light-years away, hosts debris disks that might cradle rocky planets, while Epsilon Eridani's youthful system could let us witness planet formation firsthand. But the greatest lesson lies in the voids between these stellar waypoints. The nearest stars are scattered like islands in an ocean where every mile is 1,000 times wider than Earth's diameter. This expanse isn't empty, it's threaded with rogue planets, interstellar comets, and nebula remnants that future travelers might use as stepping stones or resources. The Oort cloud, our solar system's icy fringe, could serve as a final outpost before the true interstellar dark. Humanity's stellar destiny won't begin with warp drives or wormholes, but with patience, generations of knowledge passed like a torch. The same stars that guided ancient navigators may one waymark vessels carrying our descendants. Each twinkling point isn't just a light, but a potential harbor in the cosmic sea, waiting for explorers to rewrite what it means to be from Earth. Not all stellar explosions are created equal. While supernovae dominate the cosmic spotlight, their smaller cousins, nova, offer a fascinating counterpoint where destruction and renewal intertwine. Picture a white dwarf, the dense corpse of a star like our Sun, locked in a gravitational tango with a living companion. As the dwarf siphons hydrogen from its neighbor, this stolen gas accumulates in a searing hot layer on its surface. When the pressure becomes unbearable, boom, the entire layer detonates in a thermonuclear firestorm, briefly outshining 1,000,000 suns. Unlike supernovae that obliterate their stars, nova leave the white dwarf intact, ready to repeat the cycle. The recurrent nova Ars Ophiuchi, for example, erupts every 15 to 20 years like clockwork, its outbursts visible across the galaxy as it steadily consumes its giant companion. These minor explosions pack major cosmic consequences. A single nova can eject up to 10,000 Earth masses of material laced with lithium, beryllium, and other light elements, crucial ingredients for future star formation. The famous Nova Cygni 1975 enriched its surroundings with enough aluminum isotopes to power a Geiger counter, demonstrating how these events act as celestial alchemists. Some nova even produce gamma rays, challenging our assumptions about where such high-energy radiation originates. And in distant galaxies, nova serve as vital distance markers, their predictable brightness helping astronomers map the universe's expansion with precision rivaling supernova. But if nova are stellar firecrackers, hypernova are cosmic atomic bombs. These ultra-rare events represent the death throes of stars so massive, over 30 times the Sun's weight, that their cores collapse directly into black holes with almost no warning. The energy released dwarfs even supernova by a factor of 10, channeled into narrow jets moving at 99.9% light speed. When one such jet points toward Earth, we detect it as a gamma-ray burst, the universe's most luminous electromagnetic explosion since the Big Bang. The record-holding GRB 080319b, detected in 2008, unleashed enough energy in seconds to outshine every star in the observable universe combined. Hypernova don't just break records, they rewrite physics. Their relativistic jets act as natural particle accelerators, creating conditions so extreme they briefly mimic the quark-gluon plasma of the early universe. The heavy elements forged in these explosions, like gold and platinum, are flung across galaxies at unprecedented speeds. Some theories suggest hypernova could explain mysterious ultra-high-energy cosmic rays subatomic particles hitting Earth with the force of a baseball pitch, their origins long debated. And their aftermath, not just any black hole, but a rapidly spinning magnetar or an active galactic nucleus, depending on how much material falls back onto the newborn singularity. What makes these phenomena invaluable is how they stretch our understanding of stellar limits. Nova teach us about the delicate balance of accretion and ignition on stellar remnants, while hypernova probe the edge of how massive a star can become before physics breaks down. Together, they form a spectrum of stellar violence, from the repeat offenders like T Pyxides, erupting every few decades, to the once-in a galactic lifetime cataclysms like SN 2006 Gi, possibly the brightest hypernova ever recorded. Each outburst, whether modest or monstrous, contributes to the chemical enrichment of the cosmos, proving that stars, even in death, remain the universe's most prolific architects. Stars don't just shine, they sing. Not with sound as we know it, but through rhythmic pulsations that resonate deep within their cores, sending waves rippling through their fiery interiors like the vibrations of a colossal tuning fork. This cosmic symphony is the domain of astroseismology, a field that deciphers these stellar vibrations to uncover secrets no telescope could ever glimpse. Imagine pressing your ear against the sun's surface and hearing it hum, a low, steady drone caused by pressure waves trapped inside, bouncing between its core and outer layers. These aren't random tremors, they're precise harmonies dictated by the star's structure, each frequency a fingerprint of its density, temperature, and even its age. Take our Sun, for instance, a virtuoso performer in this celestial orchestra. Spacecraft like NASA, a solar dynamics observatory, have detected millions of distinct oscillation modes, revealing details as specific as the rotation rate of its core, which completes a full turn every week faster than its surface. But the real power of astroseismology shines when applied to distant stars. The Kepler Space Telescope, originally designed to hunt exoplanets, became an unexpected maestro of stellar music, capturing the flickers of over 50,000 stars. One of its most fascinating discoveries was KIC 8462852, nicknamed Boyajian Star, whose bizarre dimming patterns sparked alien megastructure theories until astroseismology revealed its vibrations matched a normal, albeit dusty, middle-aged star, solving part of the mystery through its resonant frequencies. The parallels between stars and musical instruments are uncanny. A massive, compact star like Beta Cephei vibrates at high frequencies, like a piccolo's shrill note, while a bloated red giant throbs with slow, deep oscillations more akin to a double bass. These stellar chords aren't just poetic metaphors, they're mathematical realities. By applying Fourier analysis, the same technique used to tune guitars or diagnose heart murmurs, astronomers decompose starlight fluctuations into precise frequencies, building sonograms of stars light years away. The results astonishingly detailed interiors maps. For the red giant T Hydrae, oscillations revealed a core already fusing helium into carbon, while its outer layers remained unchanged, a snapshot of stellar evolution in action. Beyond structure, these vibrations expose stellar histories. Younger stars pulse with wild, irregular rhythms, their interiors still settling into equilibrium, while older stars exhibit smoother, more predictable oscillations, a cosmic aging metric independent of traditional brightness measurements. Magnetic fields leave their mark too, distorting oscillation patterns like a guitarist bending strings. When researchers studied the star HD 49933, they detected suppressed vibrations near its poles, betraying the presence of a magnetic field 10 times stronger than expected, a clue to how stars lose rotational energy over time. Perhaps the most profound insight from astroseismology is how interconnected stars truly are. The same physics governing seismic waves on Earth applies to pressure waves inside a star, just scaled to unimaginable sizes. This universality lets astronomers borrow techniques from fields as diverse as oceanography, where sound waves map seafloor topography, and nuclear physics, where resonance frequencies reveal atomic structures. The universe, it seems, speaks in vibrations, whether through earthquakes, sound waves, or the resonant hum of a star. As telescopes grow more sensitive, the future of astroseismology promises even deeper revelations. The upcoming Pluto mission will monitor stellar oscillations with unprecedented precision, potentially detecting quakes in stars harboring Earth-like planets. Other projects aim to catch the faint vibrations of white dwarf stellar embers, whose pulsations could unveil the ultimate fate of matter under extreme gravity. Every new frequency decoded adds another note to humanity's growing celestial score, turning the night sky from a silent light show into a grand cosmic concert, where every star sings the story of its birth, life, and eventual destiny. Long before GPS satellites circled the Earth, before compass needles swung toward magnetic north, the stars were humanity's first roadmaps, silent, steadfast guides etched across the night sky. Picture ancient Polynesian voyagers steering wooden canoes across the vast Pacific, their eyes locked not on the horizon but on the heavens. They memorized the rising and setting points of hundreds of stars, reading the celestial patterns like lines on a nautical chart. The star Arcturus, known to them as Hoculaire, wasn't just a point of light. It was a beacon signaling the path to Hawaii when it appeared directly overhead. This wasn't primitive guesswork, it was precision navigation honed over generations, where a single degree of error could mean missing landfall by hundreds of miles. Polaris, the North Star, became the anchor of Northern Hemisphere navigation because of a cosmic coincidence. Its position almost directly above Earth's North Pole makes it appear nearly motionless while other stars wheel around it. Viking sailors called it Ledastjana, the leading star, using its fixed glow to maintain course during their daring Atlantic crossings. But Polaris wasn't the only stellar guide. The Southern Cross constellation served as a polar marker for navigators below the equator, its long axis pointing toward the south celestial pole. Desert caravans from the Sahara to Arabia relied on stars like Vega and Altair to time their movements, knowing these bright summer triangles signaled safe passages between dunes when the scorching daylight faded. What's remarkable is how these stellar techniques transcended cultures. The Phoenicians, master sailors of the ancient Mediterranean, navigated by the Little Bear constellation while trading from Britain to Africa. Meanwhile, indigenous Australians used the emu in the sky, not a constellation of stars but dark patches in the Milky Way, to track seasonal changes and locate water sources. Even landlocked civilizations like the Inca carved celestial alignments into their architecture, with windows in Machu Picchu's Temple of the Sun framing the June solstice sunrise and the rising of the Pleiades, marking agricultural cycles with stellar precision. The brilliance of celestial navigation lies in its layers of redundancy. Polynesians didn't just use stars, they observed wave patterns, bird flights, and even bioluminescent plankton to confirm their stellar readings. Arab navigators combined star positions with camels, simple wooden devices that measured a star's altitude above the horizon to determine latitude. European explorers like Columbus carried astrolabes and cross staffs, instruments that translated stellar angles into geographic coordinates, though their crude measurements often left them dangerously off course. The infamous latitude voyages of the 16th century saw ships sailing due east or west along a fixed latitude until they hit land, a blunt but effective method when longitudinal calculations remained elusive. Modern space exploration still leans on these ancient principles. The Voyager probes, now in interstellar space, carry star maps etched on golden records, with pulsars serving as cosmic lighthouses, their unique pulse patterns acting as galactic GPS coordinates. The Hubble Space Telescope uses guide stars to orient its observations, locking onto specific points of light to maintain stability while photographing distant galaxies. Even the Apollo missions relied on star sightings through tiny sextants when their computer systems faltered, proving that no matter how advanced our technology becomes, the stars remain our ultimate fallback. This celestial legacy lives on in surprising ways. The global positioning system we use daily operates by triangulating signals from satellites, but those satellites themselves rely on star trackers to maintain orientation in the void. Pilots still learn celestial navigation as a failsafe, and amateur astronomers continue the tradition with handheld planispheres that map the night sky's rotation. The stars that once guided explorers to new continents now help spacecraft navigate the solar system, a testament to humanity's enduring bond with the cosmos. Every time you glance at Polaris, you're glimpsing the same unchanging light that steered generations before you, a silent promise that no matter how far we travel, the universe will always leave lights on to guide us home. From their fiery births in cosmic nurseries to their spectacular final acts as supernova or silent white dwarfs, stars are the universe's master storytellers, each phase of their existence leaving an indelible mark on the fabric of reality. Consider the iron in your blood, forged in the last desperate moments of a dying star's collapse, or the oxygen you breathe, crafted in the quiet fusion of a sun-like star's core. These elements didn't just appear, they were painstakingly assembled across generations of stellar lives and deaths, scattered through space by stellar winds and supernova shockwaves until they found their way into planets, oceans, and eventually you. The scale of this cosmic legacy is breathtaking. Every galaxy's spiral arms, those graceful arcs of light, are shaped by the collective gravity and radiation of billions of stars, some triggering new star formation by their violent deaths, others stabilizing planetary systems with their steady glow. Even the darkness between stars holds their fingerprints. The diffuse gas of the interstellar medium is laced with carbon, nitrogen, and heavier elements, the discarded remnants of countless stellar lifetimes. This ongoing cycle of creation and destruction doesn't just build galaxies, it makes them fertile. Without the carbon-rich ashes of ancient stars, Earth would lack the chemical diversity needed for DNA, proteins, or the complex chemistry that sparks life. Yet stars are more than just element factories, they're the universe's timekeepers. The oldest known star, HD 140283, clocks in at over 13 billion years old, its metal-poor composition serving as a living relic from the cosmic dawn. At the other extreme, fleeting blue supergiants like Rigel blaze brilliantly for just a few million years before meeting explosive ends. Their short lives a stark contrast to the trillion-year potential of diminutive red dwarfs. This staggering range of stellar lifespans creates a cosmic tapestry where multiple generations overlap, each contributing to galactic evolution in unique ways. A single galaxy might contain the fading glow of ancient red giants, the steady pulse of middle-aged suns, and the dazzling birth cries of protostars, all coexisting in a dance choreographed by gravity and nuclear physics. What makes this story profoundly human is how intimately we're connected to it. The calcium in your bones likely originated in the last breaths of a white dwarf's thermonuclear explosion, while the gold in a wedding ring may have been forged during the collision of two neutron stars billions of years ago. When astronomers analyze the light of distant stars, they're not just studying abstract points of light, they're reading the same elemental signatures that course through our veins. This isn't poetic metaphor but scientific fact. We are quite literally stardust given consciousness, the universe's way of understanding itself. As technology advances, so too does our ability to unravel stellar mysteries. The James Webb Space Telescope peers through dust clouds to witness stars being born, while gravitational wave detectors like LIGO listen for the ripples from black hole mergers, events that will someday seed future generations of stars with heavy elements. Citizen scientists comb through telescope data, discovering pulsars or variable stars that professional astronomers might miss. Each breakthrough adds another verse to the epic of stellar evolution, revealing how stars shape and are shaped by their cosmic environments. So when you next stand beneath a starry sky, let your gaze linger on those distant suns. Some may already be gone, their light just now reaching us across the gulf of space and time. Others are newborns, their potential yet unrealized. Together, they form an unbroken chain linking the universe's past to its future, a story written in nuclear fusion and gravitational collapse, in cosmic winds and explosive deaths. This is the grand narrative of stellar destinies, and it's one we're only beginning to decode. If these celestial wonders have sparked your curiosity, share your favorite star or cosmic question below, because the conversation about our place in the universe is just as infinite as the stars themselves.